Hello, welcome back. In this video, we'll discuss the Born interpretation of the wave function. This interpretation was given by Max Born. The wave function is generally represented with a psi. Using this symbol, we represent a wave function. The symbol is called psi. In your previous classes, you have learned about the electromagnetic waves, the sound waves, and the water waves. Electromagnetic waves, the sound waves, and the water waves. Between these three waves, there is a commonality. The commonality is a physical quantity is varying with respect to time and space. In the case of electromagnetic waves, the physical quantity is electric and magnetic fields. The electric and magnetic fields, they change with respect to time and space in the case of electromagnetic waves. In the case of sound waves, it is the pressure that changes from point to point in space and time. In the case of water waves, it is the rotation of the water molecules that establishes the water waves. But the matter waves are different from the rest of the waves that we have learned already. They are different in the sense that there is no quantity that is associated with the matter waves that oscillates with respect to time and space. All we know is matter also behaves like waves, and these matter waves, they are represented using a psi, and we cannot specify in a similar way what is actually varying in the de Broglie waves or the matter waves. Since microparticles, they exhibit wave nature, they are represented with a wave function called psi. Psi describes the wave as a function of position and time. Psi is a function of space and time, means is a function of x, y, z, t. The wave function psi has certain characteristics. The characteristics are: the first characteristic is it is a complex function, it is a single valued function, it is a continuous function, and it is a finite function. Psi must be finite for all values of x, y, z. The wave function psi has certain characteristics. The characteristics are: the first characteristic is it is a complex function. It is a single valued function. What is a single valued function? A single valued function will have one and only one value for a given set of arguments. For a given set of x, y, z, t, the wave function psi will have a single value. That is one of the requirements of the wave function psi. And the wave function psi is a continuous function. The value of the psi must be finite. It should have a non-zero quantity for all values of x, y, z. It should have a value which is not infinity for all values of x, y, z. If psi becomes infinity for any value of x, y, z, t, then it violates the Heisenberg's uncertainty principle. Therefore, psi must be finite for all values of x, y, z, t. Now we shall look at the probability-based interpretation given by Max Born. We have seen that the de Broglie waves can be expressed using a wave function psi. We have also seen that psi is a continuous function, it is a finite function, and it is also a complex function. Since it is a complex function, psi cannot give any information about the particle. However, it will have all the information describing the particle in that particular state. Here the state means a set of positional coordinates, component of the momentum, component of the angular momentum, energy, etc. So a set of these physical quantities, they describe a state and it indicates the state of the particle. According to Heisenberg uncertainty principle, we can only know the probable value in a measurement. Therefore, the probability cannot be negative. Hence, psi cannot be a measure of the presence of the particle at any location x, y, z. But it certainly indicates in some way the presence of the particle around that particular location. However, psi certainly indicates the presence of the particle around x, y, z at any given instance of time t. The probability interpretation of the wave function was given by Max Born in 1926. Max Born interpreted the wave function as the square of the magnitude of the wave function's mod psi square evaluated in a particular region presents the probability of finding the particle in that region. The Max Born interpretation is that the square of the wave function mod psi square evaluated in a particular region represents the probability of finding the particle in that region. This kind of an interpretation of the wave function has a direct relation with the Heisenberg uncertainty principle. We know that in the Heisenberg uncertainty principle, we have said that for each measurement there is going to be certain amount of uncertainty. So the value that we get is a statistical value. Max Born states that the square of the wave function psi square evaluated in a particular region represents the probability of finding the particle in that region. In other words, probability P of finding the particle in volume element dV, which is dx times dy times dz, is proportional to mod psi x comma y comma z square dV at time t. Therefore, we write P is proportional to mod psi x comma y comma z square dV. Here, mod psi x comma y comma z square is called the probability density, and psi x comma y comma z, this is called the probability amplitude. Since we know that the particle is certain to be somewhere in the space and time, so the probability P will be equal to 1 when we integrate mod psi square dV over the entire space, meaning integral minus 2 plus infinity mod psi square dV is equal to 1. Since we know that psi is a complex function, we can write mod psi square as integral minus 2 plus infinity psi star dV is equal to 1, where psi star is the complex conjugate of psi. Therefore, we say that psi has no physical meaning. However, mod psi square gives the probability of finding the particle. Now we shall discuss a condition that is connected to the wave function psi, which is known as the normalization condition. We have said that mod psi square gives the probability of finding the particle in a given region. If at all a particle exists, then it must be somewhere in the entire space. Since we are sure that the particle must be somewhere in the space, the sum of the probabilities over all values of x comma y comma z must be unity or equal to 1. If psi x comma y comma z comma t is the wave function of a particle that exists in space, then when it is multiplied by a constant c, we get psi n x comma y comma z comma t that satisfies a condition. The condition is psi n of x comma y comma z comma t is equal to the constant c times psi x comma y comma z comma t, where psi n satisfies the following relation. The relation is integral minus 2 plus infinity mod psi n x comma y comma z comma t square dx dy dz is equal to mod c square integral minus 2 plus infinity mod psi x comma y comma z comma t mod square dx dy and dz. And this must be equal to 1. The reason is the particle should be somewhere in the entire space. Here, the wave function psi n x comma y comma z comma t is called as the normalized wave function, and the constant c is called the normalization constant. Therefore, we write mod c square is equal to 1 over integral minus 2 plus infinity psi x comma y comma z comma t mod square dx dy dz. Here psi n x comma y comma z comma t mod square dx dy dz is called the probability density. So whenever the wave function is normalized, psi square dv equal to the probability of finding the particle in an element dV. So we write P is equal to mod psi square dV. What is P? P is the probability. What probability we are talking about? We are talking about the probability of finding the particle in a volume element dV. In this video, we have started by stating that the wave function is represented by psi. Its interpretation is given by Max Born. And we have said that matter waves are represented using a psi, and the psi is generally called as the wave function. We have seen the characteristics of wave function psi. We have said that psi is a complex function, it is a single valued function, it is a continuous function, and it must be finite for all values of x, y, z. We have seen the probability interpretation of the wave function given by Max Born. Psi certainly indicates that the presence of the particle around a point x, y, z, t. The Max Born interpretation states that the square of the wave function mod psi square evaluated in a particular region represents the probability of finding the particle in that region. So the probability P of finding the particle in volume dV is proportional to mod psi square dV. So we have seen what is probability density, and we have also seen the probability amplitude. We have said that mod psi square is nothing but psi star, where psi is a complex function. We have seen the normalization condition. We have said that C is the normalization constant. We have seen how to obtain the normalization constant, and we have said that the probability of finding the particle is given by mod psi square dV. Thank you.